So here, as we continue the rest of the video, now we have to talk about phase 4 isovolumetric relaxation. So now we discussed that ventricles ejected blood in the third phase. So that was actually a ventricular ejection phase, and phase 4 isovolumetric relaxation. And here, after the ventricular systole, the ventricular muscles start to relax. AV valves and semialveolar valves both are closed. There is no apparent volume change, but the pressure inside the ventricles gradually falls, making it an isovolumetric relaxation. So now AV valves are closed because blood has been pumped into aorta and aortic pressure increased more than the pressure inside the ventricles. So that is why semialveolar valves have been closed because of that reason, and atrial valve, ventricular valves are closed because at the um, ventricular isovolumetric contraction phase, because the after pump atrial systole or the diastole of the cardiac cycle phase 1, the pressure inside the atria was lesser than the pressure inside the ventricles. So because of that, atrial valves closed, giving out the first heart sound, right? There is no apparent volume change, but the pressure inside the ventricles gradually falls. Now there's no volume change because both the valves are closed. Semialveolar valves are closed, semialveolar valves are closed, and AV valves are closed. So because of that reason, no volume changes, but the pressure inside the ventricles gradually falls, making it an isovolumetric relaxation. After the isovolumetric relaxation, the next cardiac cycle begins, right? So, when isovolumetric relaxation takes place, after a few moments, then we will go back to phase 1. Phase 1 means diastole, that means where the ventricles are relaxing but blood gets filled into the atria, and then AV valves gets open and blood gets passively filling into ventricles first, 70% passively filled, and then again the rest of the 30% will be filled by the atrial systole by contraction of atria. And after that, and phase 2, it was the isovolumetric contraction phase where the blood is filled into ventricles and the valves are closed, and then keeping the ventricle volume constant, the ventricles try to contract and then increase the pressure within itself. And then the third phase, ventricular ejection phase, what happens is that this pressure within the ventricles goes higher than the pressure inside aorta, and then the semialveolar valves open and blood gets ejected into the aorta and respectively to the pulmonary artery and then pulmonary vein. Then this in the phase 4, what happens is these ventricles relax again. AV valves are now closed and semialveolar valves are again closed, right? So as the pressure starts to drops within the ventricles, these valves are closed, and then isovolumetric relaxation means keeping the volume the same. The this ventricle started. So it is said that it's not that all the volume is pumped out, but you saw that only 70 to 90 milliliters of blood has been pumped out. 50 milliliters remain out of that, right? So yeah, 50 milliliters remains. 70 to 90 milliliters only pumped out. So 120 milliliter is the ideal end-systolic volume. So the ideal end-systolic volume is 50 milliliters is the end-systolic volume. So you get the difference as 70 milliliters. So 70 milliliter is the stroke volume, right? So pressure volume what I was trying to tell is end-diastolic volume is 120. That means the blood that has been accumulated in the ventricle at the end of the diastole. That means after first diastole, right? That means after the AV valves are closed. Then before the AV valves are closed. Then 50 milliliters is the ESV. That means after semialveolar valves are closed. So what has been pumped out is the difference between them. That is 70 milliliters. That is called stroke volume, right? That happens in ejection phase. Then pressure volume loop of left ventricle DA. During diastole, the pressure increases. So you can see that pressure is increased. DA during the diastole, the pressure increases. AB during isovolumetric contraction, pressure sharply rises without a volume change. Right? During diastole, the pressure increases. During isovolumetric contraction, pressure sharply rises without a volume change. During isovolumetric contraction, pressure sharply rises without a volume shift. So you can see during the diastole, pressure increases in the left ventricle, right? So because blood gets filled in. Then during the isovolumetric pressure is increasing but there is no volume shift. Then BC ventricular ejection means blood pressure drops and also the volume drops, right? It just first climbs to a maximum, then after that it drops. Then C to D ventricular isovolumetric relaxation means pressure drops rapidly but volume is constant. So what differences can be observed in the cardiac cycle during expiration and inspiration? What are the differences that can be observed to the cardiac cycle with the bradycardia and tachycardia? So during inspiration and expiration, what are the differences that can be observed? And what are the differences that can be observed in the cardiac cycle, bradycardia, and tachycardia? Okay, let's actually think about this. So if you think about bradycardia, that is slow heart rate. Slow heart rate means we should actually go and we'll look into another video in this one. So now we'll talk about jugular venous pressure tracing. So you can see this is atrial contraction. I told you in the atrial contraction you can see A wave because this uh, um, yeah, not A, right? um, so if we talk about the atrial contraction, A wave, so A wave is when the bulging of the um, bulging of the atrioventricular valves towards atria because they're during the contraction, right? When in the injection phase, right? So blood is pumping from the ventricles to aorta. This atrioventricular valves bulge the into the atria, so that gives out a C wave, and this is atrial filling. So atrial filling, yeah, I think this is actually wrong. Right? Peak pressure in right atrium just before opening of the tricuspid valve. Opening of tricuspid valve followed by passive emptying of artery. Okay, let's leave this and go to the next one because there's some doubt regarding this atrial jugular venous pressure tracing. I will clear them in the next video. Heart sounds and murmurs. Heart sounds and murmurs. So, sounds that can be heard over heard over the precordium on over the pericardium on osculation, right? So, two main heart sounds, first heart sound and second heart sound. Two other heart sounds that may or may not be heard are third heart sound corresponds to rapid ventricular filling during diastole. Fourth heart sound always abnormal can be heard in disease condition shortly before the first heart sound. So to get these heart sounds, or we get the five positions where we can get this heart sound. So this is the aortic area, second right intercostal phase. So this is the first intercostal phase. This is second right. Right means the right side of the body. This is second right intercostal phase. This is the pulmonic area, second left intercostal space. So we call this pulmonic area. This is aortic area, right? The third one is Erb's point. Third left intercostal space is Erb's point. So it also left sternal border. Tricuspid area, fourth left intercostal space, left lower sternal border. Fifth mitral area or apex, fifth left intercostal space, mid-clavicular line, mitral area or apex, fifth left intercostal space, mid-clavicular line. So the murmurs, abnormal or normal sounds due to the turbulent flow can be systolic. Between S1 S2 can be normal or abnormal. Diastolic S2 and S1 always abnormal. Continuous heard throughout the cardiac cycle. So there are three types of murmurs. Systolic murmurs that can be either normal or abnormal between S1 and S2. Diastolic between S2 and S1 always abnormal, right? And this is stage 1, right? Stage 1 and stage 2. So that means yeah, systole is atrial systole. So continues her throughout the cycle. So now we are going to get these murmurs, right? So the systolic murmur we obtain through aortic area. So aortic stenosis, flow murmur, physiological murmur, aortic valve sclerosis. So these are the types of diseases where we can find this aortic or systolic murmur, right? So aortic stenosis, flow murmur, physiological murmur, and then aortic valve sclerosis. Then pulmonic area, systolic ejection murmur, pulmonic stenosis, atrial septal defect, flow murmur. Tricuspid area, polysystolic murmur, tricuspid regurgitation, ventricular septal defect, diastolic murmur, tricuspid stenosis. Mitral area, polysystolic murmur, polysystolic murmur in the mitral area, mitral regurgitation, just bulging of the mitral valve into the atrium. Systolic murmur, mitral valve prolapse. Diastolic murmur, mitral stenosis. Erb's point, diastolic murmur, aortic regurgitation, pulmonic regurgitation. Systolic murmur, hypertrophic cardiomyopathy. So you can see these are the sound murmurs. So you can see crescendo systolic can be crescendo descendo, draw polysystolic, they can be left and right. On the left and right there are different diseases, and diastolic you can descendo and descendo crescendo. Those types are here. So the results are also given here. So this is diastole, this is ABCD. So you can see this sounds right. Thank you. We'll join in on the video.